Okay, so inference for logistic regression is almost identical to inference for ordinary regression. Okay? In both cases, the first step is going to do the overall test for the collective effect of all the betas. We're looking at inference for multiple logistic regression here. So our null is that all the betas, all the slopes in front of the x's, we're not talking about the intercepts, but the slopes in front of the x's right here are 0. That they're all 0. There's nothing in our model, in the population, right? In the population, these slopes in front of the x's are all 0. Our model tells us nothing. And our alternative is, that we have some signal in here, and at least one of those betas is non-zero. Okay, so that's the idea. And then in ordinary regression, ordinary linear least squares regression, we had a quantitative y, right? We were predicting things like exam scores. So what we could use was either a chi-square or an f-test. We have multiple slopes, so we can't use a z or a t. But we could use we used an f-test for small samples, and then we said when n got big enough, we could use a chi-square test. We could do either of those. But now we're predicting a 0, 1 y variable. We're basically predicting counts, or percents, like the percent. Instead of your score on an exam, let's say the percent of you who get an A on the exam. So we're predicting 1 if you got an A, 0 if you didn't. Success or failure. 0, 1. And for predicting counts, we never use f-tests. Because why? Because we always use f and t's when we have unknown standard deviations. But when you're predicting counts, you can get the standard deviation directly from the count. For example, if our sample data said that looked like 50% of you got an A, okay? 50%. Well, directly from that 50%, it's a count, how many people got A's, and 50% of you did. And then I could say, okay, right from that not only tells me the mean, that 50% of you, half of you did, but it also tells me the standard deviation, right? Because all I have to do is say, the standard deviation would be p times 1 minus p, and then you take the square root of that, which would be a half. So the probability distribution, including the standard deviation, is determined directly from the predicted counts. That's how it is for a chi-square test. That's unlike f or t tests, which, remember, estimate those standard deviations. That's why we have those degrees of freedom based on the sample size minus how many parameters. That's all because we're estimating standard deviations from the variation in our sample and not from the predicted mean itself. The predicted mean tells you nothing. Like if I'm doing an ordinary least squares regression and the sample data says that maybe the average was 80% score on the exam, that doesn't tell me anything about the shape of the distribution or the standard deviation. Okay? So, point being that we're not going to use these Fs. We never use f-tests here. We're just going to be using the chi-square distribution. And we did this before with simple. We showed how it's very similar to a chi-square test. Okay, now the probability, let's see. Now what about the degrees of freedom? The degrees of freedom are just like we've had before for chi-squared. It's the number of x's, or the number of parameters in the model, the number of these little b's, parameters, including the intercept, minus 1. Okay, so why don't we write this down so you remember? And the degrees of freedom are equal to, just like as usual, the number of parameters minus 1. So these are the parameters. That's the same, there's one intercept, so that's the same as the number of x's in your model. All right, now, what else do we need to talk about here? Let's see. And then what we're going to do is, after we do this overall test for the collective effect of all the slopes, for just like we usually do, then we're going to say if we reject the null, we reject this null that they're all equal to 0, we reject that, then we know at least one of the slopes is non-zero, and then the next step is to test those individual slopes. And to do that, with ordinary regression, we used an F or a T, but now, we used a T or a Z, or an F. But now, we're going to just use the Z. And we could use a chi-squared, but we're just going to use the Z. We can't, point being, you can't use T or Fs for the same reason that I just explained here, because you just don't do those for counts. We never did it when we had percent problems, right? Because we know the standard deviation. We don't need we don't have to use the variance of the sample. Okay, so that's important too. You never use t-test, which makes things simpler. You don't have to worry about those degrees of freedom. Okay, so then what is this difference between, what's the difference between the ordinary and logistic regression? It's how we estimate these betas in the model, how we estimate those. And instead of doing our usual least squares, where we take the sum of the squared residuals, we estimate them by a maximum likelihood estimate, which maximizes the likelihood of getting our sample data. Now, with ordinary least squares, these two things are the same. So it really doesn't matter which way you do it. If you take STAP 400, I'm sure that's probably one of the things you've proved. But for logistic regression, they're not the same. So we're not going to be doing least squares. We're going to be maximizing the likelihood and using this deviance table, the same as minimizing the deviance. And if those of you who are more interested in the math behind this, you should read, if you're interested, see week 13, where we explain it in our free R course. It's on our homepage. And go to the lessons page and go to week 13, and it will be all explained. Plus, you can learn R really in depth if anybody wants to for free. It's just the course that used to go along with this course before I revised this course. Okay, so now it just deals with the second half of this course. It doesn't deal with all the STAT 100 stuff. All right, so now we already looked at this deviance table. You can turn the page right here. We've done that. We already looked at this. And we saw how we're going to really, even though we're going to get, it looks just like an ANOVA table, but it's really an analysis of deviance. This is the analysis of deviance. And what we said was that, and here's it looks just like our ANOVA. Here's the sum of squares for the model. Right here, this is our deviance, and this, we said, is distributed as n gets large as a chi-square. And that's why we're using this right here with 2 degrees of freedom. Why? Because we're going back to that example that we just finished up last time that had 2 predictor variables. We're trying to predict whether somebody, a 0-1 variable, getting into med school or not, based on your gender and what? Your biological science score. Okay? Remember that we have 3 betas here, right? 3 of them. So our parameters are equal to 3. That means our degrees of freedom, parameters equal to 3. That means our degrees of freedom are 2. That's why this is p minus 1. It's the same in this little chart. This is from our data program. I also write the number of x's because those are the same. We just don't count the intercept. Okay? And it's distributed as a chi-squared as n gets big, and the limit it is. Okay? So now what we're going to do is do a chi-squared test then on first the overall. To test the overall, we're going to do a chi-square test, and then we are going to test these individual slopes with z. And they're already done for you here, and we're going to build confidence intervals. They're already done. We're just going to see where these come from. Okay? Let me just make sure I covered everything on this page. All right. We talked about why we do these likelihood procedures. We didn't really talk about how, for continuous x variables, think about how problematic it would be to do least squares on the log odds. A continuous x would give you, for your observed y, you're always going to get a 1 or a 0, right? That's all there is. The y's are always 1 or 0. So when we put it into the log odds form, we'd have what? We'd have the log of 0, which is negative infinity, or we'd have the log of 1 over 0, which would be positive infinity. So our log odds would be, how could you minimize the squared error of these predicted log odds? It would be like trying to fit a bunch of infinities with the least squares line. It wouldn't really work at all. So what people do, you might think is what you do, and what we did do when I showed it on the data program, was group them, right? Do these groupings. Don't use all the actual y's and minimize their errors, but group them so we get the percentage within any vertical strip, right? Within any grouping, the percentage of ones. We could do that. Then we wouldn't have to fit a bunch of infinities, but then our fitting results would depend on how we do that binning, how we do that, and it messes things up. And the other problem is we could try to just minimize these observed 1s and 0s minus these predicted, once we bin them. But it just, as we saw before, it would just fit in the middle of the data. We really are interested in the ends here. It wouldn't be sensitive to the very low probabilities and the very high probabilities. If you think about it, for rare events, if you, here you're trying to, I'm not sure if you're interested in this, but you'd see that, for like probabilities of just 1 out of 100 versus, what do we have here? 1 out of 10 to the 5th. It looks, it's not going to make much difference, but look, it's so much more likely to get a 1 if your probability is 1 out of 100 rather than 1 out of 10 to the 5th. So doing a maximum likelihood is very sensitive to those extreme values and fits all the data, not just the data in the center. Long story short, you can read a lot more about it if you go to this lessons page if you're interested. But for now, we've got enough tools, and I think you've got the intuition to go ahead and proceed. So that's what we're going to do. So here we are, and what we're going to do. Okay, so we're looking at this, and here's our fitted model right here for our sample data, and let's state our null. We're going to do the overall test. So H0 is what? That even though in the sample we have non-zero betas. We're not interested in this one. We're just interested in these two. Even in the sample, they're not zero. Our null is that in the population, the whole population, imagine a wider population, that both of those, this is beta 1, this is B1 and B2 from our sample, and we're estimating, we're saying in the population, the beta 1 and beta 2 are really zero. These are small and just due to the luck of the draw. And our alternative is, this is our usual null and alternative that we always do, and our alternative is what? That no, in the population, our alternative is that at least one of those is equal to 0. So in the population, the null is always the strict null is for the collective effect of all these slopes. And so let me just write this out just to make sure it's what we always do. It's in the population. The slopes are all 0. That means that no matter what gender you are or what your biological science score is, it makes no difference in you getting into med school. Now that seems crazy with the biological science score, and we're going to reject this. I just want to show you the test. The idea is that we just happen to observe non-zero slopes due to chance variation. You're not going to get exactly 0, so these slopes are small and just due to chance. Okay? And that the alternative is, it's not due to chance. It's because in the population, one of them really is not 0. Okay? These are too big. And look, we've already done the test and the p-values are so small. These are too big to be due to chance variation. So we assume this null, like we always do. We assume the null, and we say that when the null is true, this test statistic, our chi-square statistic, follows a particular distribution that with 2 degrees of freedom, so this is we've got these 2 degrees of freedom here, and we've got this statistic here. That's our chi-square stat. And that's our degrees of freedom. Okay? And now we know that it's going to look something like, when the null is true, it's going to look something like this. All right? Like, it's not going to be symmetrical. This is the distribution of the chi-square statistic when the null is true. So when the null is true, if you remember, the mean is about 2, and we got this huge chi-square statistic. So let's just look at our chart to refresh our memory for the chi-square, and you'll have this on your exam. Here it looks more symmetrical because it's showing one with more degrees of freedom. But for 2 degrees of freedom, it's pretty asymmetrical. And here it shows for 5%, if we wanted to do a 5% cutoff, we just need a chi-square beyond 5.99. If we want to do a 1%, it would be beyond this. But look, ours is 9.33. So that's even bigger than this one. Okay? So we can draw that. It's basically off the page, and I can't make it go down small enough. Basically there's almost no area. Here is our chi-square statistic. Right here. This one that we got. It's the same thing. And that's why our p-value is so tiny. It's less than 0.005. It's almost 0. Okay, that's why our p-value is so small. And if you didn't, and you could compare it to, and on the chart, this is 29.33. That's our chi-square. We could compare it to those critical values we just saw. At 5% critical value, we had something like, this is, let's say, this was at, when I said all this area is 5%. We had a critical value, I'll put a little star, of 5.99. And ours were well beyond that. And then we even said at, what did we say, at 0.1%? That it was 13.82. So let's just draw that in somewhere. So here's the 1% cutoff. These are just cutoffs. These critical values are just cutoffs. These are just null cutoffs. And that's the 5%. Beyond that, you'd have a p-value of less than 5%. Here's the 0.1 cutoff, 0.1%. That's 0.001, right? And that's the chi-squared critical value is 13.82. So we know ours is less than that, so we're rejecting this null big time. If the null was true, we'd just see this once in a blue moon. Very, very, very rare event. So well beyond a reasonable doubt, our p-values, the doubt is so tiny, we're going to reject. So we reject the null. So where should I write this? We can just say reject null. Because p is almost 0%. So we can reject it certainly at the 0.1% level. And conclude that at least one of our slopes, and can go with the alternative right here, that at least that we have some significance here. This model has a signal in it that's predicting whether people get into med school or not. It's telling us something. And conclude at least one slope is significant. All right. So now we're ready to test the individual slopes, and we're going to do that with z-tests. So let's do that. And it's already done for you right here, but let's just go through it. To test whether the individual slopes are significant, we do z-tests, not t, because we're doing counts. State the null and alternative for each slope, calculate the z-score and the p-value. It's already done, but let's just check it. All right, our h naught. Now we're just looking at one slope, so we don't have to, we can use z-tests. We don't have to use chi-square tests. We can just do a simple z, which makes it easier for us. Okay, so we'll do it for gender first. Let's do the gender slope first. That one. And what is it? We're saying even though we see this in our sample, this slope, that in our population, beta 1 is equal to 0. Okay? And our alternative is what? Why am I switching these alternatives? Sorry, I'm not being consistent. Sometimes I use a capital A and sometimes I use a small a. I should be consistent. People use either one, but I should be consistent. All right, and this next one is what? Now, I think I'll do two-sided because, why? Because it's two-sided because we didn't really know, we didn't state our hypothesis ahead of time. Because I wasn't sure whether, at this point I'm not sure whether it's going to favor males or females. Because we didn't state hypothesis ahead of time, what we thought it was going to be before we looked at the data. I'm just not sure which direction it's going to go to. Okay, so let's work on this then. So what do we do? Well, z, as usual, is what? Z is the usual observed slope in our sample minus the expected slope from our null, which is 0, over the standard error for the slope. Okay, so let's do that. Our observed slope is right here. That's what we got here. It's this. Is 2.015. Our expected is that. We'd expect from the null, as usual. And our standard error is given to us right here. So it will be given to you. You're not going to have to compute them. So there it is. And that's how they got the C-score, right here. 2.348. And they already did the p-value, but let's just check it, okay? And we can see if it's a one-sided or a two-sided p-value. So we'll just draw the picture here, right here. This is as a z. We expect 0. And as a z, we got 2.348. Let's look that up. 2.348. Here's 2.35. Why don't we just round to 2.35 and do 98.12? So that's 98.12 in the middle. Between, I'll just round this. Round to 2.35. All right, between 2.35 and negative 2.35. All right, and negative 2.35, and that's what we got. So, what is our p-value? Our p-value is going to be 100 minus 98.12. And here, let's just to make it more intuitive, that's what it's going to look like as a z-score, but what does it look like as a slope? As a slope, we also expected 0, but our observed was 2.015. And that lines up with 2.35. We happened to get, okay, so we got on this side, but we did it two-sided, so we should include both sides. So our p-value is what? Our p-value is 100 minus 98.12, which is 1.88%. These two together. So they did a two-sided here. So they did a two-sided too. We rounded a little bit, but we got exactly the same thing. Any questions on that? Do you want me to do the other one too? It's done the same way. They also did a two-sided here. I think I wouldn't do a two-sided here because I think it doesn't, I would just divide that in half. Why? Because don't you think the alternative, we could hypothesize ahead of time and say that we think that raise a higher biological science score is going to help you get in, not hurt. So we could make a directional alternative a greater than sign. Does anybody want to see me do that, or can we just move on? Raise your hand if you want to see me do it. Okay, let's just move on. It's just the usual. All right. Now, we're going to do confidence intervals for the slopes. Okay, so let's do that. And so what are they doing here? Okay, so this right here is our z star. The computer is using 1.96, so that's the critical value of z star for 95% in the middle on the normal curve. So that's what they're going to be using. They're going to be building confidence intervals. We often round to 2. We usually round to 2. And I'll tell you which you do on the on the final. It's all multiple choice anyway. But just because we do it in our heads, we usually round to 2. But I'm just going to follow the printout here. Okay, so this is just, you know this already. We've done it a zillion times. What is this 95% confidence interval, and what's happening here? And why am I running out of ink? Okay, so this is 0 in the middle, and on the normal curve between negative 1.96 and positive 1.96 is 95% of the data. And so what we're saying is that when we reject the null, or when our confidence interval doesn't include 0, it means our z fell here or here. Okay? There or there. And let's look. Yes, it fell here, and it doesn't include 0. It's not including 0. All right, we build confidence intervals for the slopes the usual way. What is our usual way? We just take the sample slope plus or minus 2 standard errors for the slope, and that's exactly what was done here. So we just took this and added and subtracted 2 of these to it, and subtracting 2 gave us that, and adding gave us that. That's how we build confidence intervals for the slope. But how about for the odds ratio? We want to build a confidence interval for the odds ratio, so we have to do it in a 2-step process. And that's what I'm showing here. So let's go through and do that. And you've already done almost the identical thing with log transformations. All right. So let's just write this down. To build confidence intervals, we first find the endpoints of the confidence interval for the sample slope. All right, so we're going to do that first. So we're going to say a 95% confidence interval. This is for the slope right here, is going to be just that, 2.015 plus and minus the 1.96 here. And then times the standard error. So let me just do this. There's your 1.96 and there's the standard error. Okay. And that's where they got these 2 numbers. So this is equal to the lower limit. When you subtract 1.96 times the standard error, you get this lower limit. And here's our upper limit. So the idea is it doesn't include 0, meaning that when we went all the way, we must have landed here, somewhere beyond here. So that when we go take 1.96 times the standard error, this is on the z, but we'd have a slope here. So our two point, it's on this picture right here, right? So if we go 1.96 times the standard error, we don't capture 0. Our lower limit doesn't capture 0 because we're outside. If you go we're outside here. So if you multiply by 1.96, these are standard errors, 1.96, you end up here. You end up somewhere where you don't include 0. Okay? That's all that is. So that's our first step. Now, our second step is what? We're really interested more in this odds ratio because it's so intuitive. Remember, people don't think in terms of log odds so easily. So we want that odds ratio so we can figure out the odds. Okay, for one comparing males to females, we want to get the odds of the odds ratio, okay, which, remember what it was. It was e to the 2 point, okay, so here, let's just do it and you'll see. 95% confidence interval for the odds ratio for gender. So we're doing a 90, I should write this down here somewhere. Okay, so let's just write this down. What we're doing is we're making these point estimates. We got the point estimates for the slope is 2.015. This is for gender. And the and then we have this estimate for the odds ratio, which is e to the 2.015. And we did that last time. We said that's 7. Was it a 7.5? Is that what we got for the odds ratio? I think we did. Okay, 7.5. Remember last time? If you do that out at 7.5. Okay, so now we can't just say, okay, 7.5 plus or minus something, because it's not symmetrical. What we have to do is we have a log odds here, and we exponentiate that. So we're going to exponentiate those endpoints. So we'll get e to the 0.331 all the way to e to the 3.696. And we get this confidence interval that's going to include the 7.5, but it's certainly not going to be symmetrical around it. What is it symmetrical around? To check this right here, what you would do, if we wanted to check it, we wouldn't see that it's in the center here. We'd see whether it's the geometric mean of these two, right? So we'd see whether 1.4 times 40.29 is equal to 7.5. That's what we'd check. Okay? But this is our point estimate, and this is our margin of error rounded. And it's not plus or minus something. It's always much closer to the smaller one. So that's what we're doing here. So it means that we're 95% sure that the odds for females getting to medical school in this model are between the odds compared to males. We're 95% sure that the odds for females getting into med school compared to males, the odds ratio, female odds divided by male odds, is between 1.4 and 40.29. Okay? So that's hard to see. The odds ratio, not the odds. So what is that? The odds ratio. That means the odds of females getting into med school divided by the odds of males. So it means that the odds ratio, it means that females have somewhere in that range (1.4 to 40.29) times higher odds of getting in, given that they have the same biological science scores as men. I didn't write that very well. Given the same BS scores. That's what it means. Now we'll do the same thing here for the biological science score. It's exactly the same. So we'll just take our point estimate for biological science, which is right here, add and subtract about 2 standard errors, and we'll get this, and then we exponentiate those. That's all we're doing. So we can do that. Okay, so the first step is the 95% confidence interval for the slope. And that is super easy. It's 1.66 plus or minus 1.96 times 0.4629. And then we get this. Sorry, I'm doing it so long-winded. That's what we get. So we get that, which is 0.7525 to 2.567. That's our step 1. Then step 2, I'll do it down here. Step 2 is the 95% confidence interval for the odds ratio, and that's just raising these right here. All we're going to do, I could just do the odds ratio confidence interval for this. Odds ratio for BS. Why don't I just do it here? The odds ratio would be e to the 1.66, and then you just raise e to the 0.7525 and e to the 2.567. That's what it is. Okay, that's all I'm doing. So it's e to the 0.7525, e to the 2.567, and that's all it is. And when I did it, I got 2.12 all the way to 13.03. Okay, any questions on this? So now I'm going to ask you, well, let's just fill this in right here. So did I say this wrong too? This means that we're 95% sure that the odds of getting into med school based on this data, no, that the odds ratio, we're doing it for the odds ratio, we're 95% sure that the odds ratio is between 2.12 and 13.03. This means that what? The odds of acceptance are in that range, or somewhere are between 2.12 to 13.03 times higher for each additional point, each extra BS point. Given you're comparing two people with the same sex. Two men or two women. Oh boy. Okay. That's exactly what we did before. And anybody have any questions on this? So now, the next question says what? The odds ratio confidence interval not containing what is the same as the slope confidence interval not containing 0, and to rejecting the null, that the slopes are 0. Maybe we should do this as an iClicker. Let's go to the iClicker, and let's do that. And this is, probably a likely question, something like this on the final. So think about it. The two-sided value for the gender slope in the log's odds equation was less than 5%, right? We got that. We just did that. So we rejected the null. And we can conclude that we concluded that the slope didn't have the 95% confidence interval for the slope did not include 0. So what do you think about the odds ratio? Do you think that does not include 0 too, or do you think that's something else? Look, we know gender's significant. We know that females are being favored, right? So, do you think that we conclude, we rejected that they have the same odds? So if you reject they have the same odds, what does that mean to have the same odds? Does that mean your odds are 0 to 0? If you have the same odds, the null is they have the same odds, same probability of getting in. Same odds means what? Their odds are 0? Their odds are 1 to 1? Or their odds are 0.5? What do you think it means? If somebody has the same odds, you say 50-50. That's, what is that? 1 over 1. Odds are 1 to 1. That means they're the same, right? Doesn't mean they have 0 to 0 odds or 0.5 odds to 1 odds. So what do you think? Okay? Think about it. I gave a lot of hints. We're going to stop it. And I hope you said D. You did win out. D was the best. Okay. It means it does not include 1. Let's write that down. Let's go to the document camera. And it's really hard to see this, but it says the odds ratio not containing 1 is equivalent to the slope not containing 0 and to rejecting the null that the slopes are 0. Why? Well, what should we say? Well, I'll just do, maybe math will help. If the slope in the log odds, the slope does not contain 0, then the odds ratio, which is equal to e to the slope, does not contain e to the 0, which is 1. That's maybe that math would help. But the idea is that the null is, remember what the null is, that there's no discrimination, that knowing somebody's gender doesn't tell you a thing about whether they're favored to get into med school or not, okay? We're rejecting that null. We're saying that there is favoring female, right? So we're rejecting that their odds are 1 to 1. The null would say their odds are the same. Their odds are the same. The odds ratio is the same, 1 to 1 odds. The odds of the females compared to the odds that they have the same odds. Odds ratio is odds of females over odds of males. Okay? Oh, all right. Let's move on. This is the kind of thing that, look, I don't blame you at all. It's actually the hardest type of thing. These conceptual questions are harder, and you'll just, don't worry, it's just because you don't have a lot of practice with them. The more you do it, and after you do the practice exam, it's going to come to you, and I don't expect it to come to you on iClickers. I just want you to start thinking about it. Okay? So don't feel bad. Don't get worried. It will come to you the more you do these problems. I guarantee it. So here's the summary, and please read it all.